Probably most of you are familiar with limit equilibrium. I'm sure you all did this in university. Probably all own a copy of Slide or GeoSlope or something like that. I'm sure you know how it works better than I do, where it takes the slices and does load balancing and so on. Figures out the surface, which produces the minimum factor of safety. We don't do that. We don't have limit equilibrium software. This is not built into FLAC2D. We do something else. So what FLAC2D and FLAC3D do is this shear strength reduction approach, which you may or may not be familiar with. There's a full solution, changes the properties, does the full solution again to see if it's stable, changes the properties, does the full solution again to see if it's stable. Keeps on doing that until you get to factor of safety. So there's a bunch of slides here trying to convince you that this is better than the limit equilibrium approach. There are certainly reasons why it is better. It's definitely slower because it's running multiple FLAC2D analyses, but it's more general, more effective, essentially solving the true problem rather than just doing these slices. In 2D, this is a realistic approach. I mean, in 2D, you can run these factor of safety analyses with the shear strength reduction model, and it goes in a reasonable amount of time. 3D, it's not really realistic. So if you haven't seen it before, this is the way it works. You essentially take the shear stress divided by now which way is it? I gotta see if I get it right in my head. The actual shear stress goes on the bottom, and the shear strength goes on the top. Essentially, you take the actual shear stress and divide it by the shear strength, you get some factor of safety, and you just keep messing with it until you just keep messing with the shear strength until this thing fails, and then you know what the factor of safety is. And this is just showing a picture of what's happening here. So we're simultaneously reducing the cohesion and the friction, right? So that the curve gets shallower and the intercept changes. So you can just think of it as taking this curve and gradually dropping it down until this thing fails, and then you can figure out what the factor of safety is. It's possible to just reduce the cohesion. So you're doing this, you're dropping the line down, or just reduce the friction. So you're just rotating the line. I've never actually seen anybody do that in reality, but it is possible. So this is just a slide telling you why it's a good idea to do the shear strength reduction method rather than limit equilibrium. Yeah, satisfied everywhere, computed everywhere using field equations. Crucially, it gives you deformation. Limit equilibrium gives you a factor of safety, but it doesn't actually tell you what the deformation is. It tells you, shear strength reduction tells you a little bit more interesting information about the failure surface and potentially more than one failure surface. We have an example of that in a minute. The mechanisms that develop satisfy kinematic constraints, not necessarily true in limit equilibrium. Having said all of that, of course, there's a time and a place for limit equilibrium. Certainly, if you want to run a whole pile of models quickly, it's totally useful. If you want to get sort of more accurate results for a particular model or a few models, shear strength reduction is a good choice. Right, so this is just a little detail about how it works. Cohesion and friction are reduced by trial values. Factor of safety as value, and okay, we don't want to go into all this stuff. We can just draw it on the board. The way it basically works is, so you start out with factor of safety of 1. So you take the model as it is, run it. So this is 1. Okay. Run the model. Hopefully it's stable, right? And then it says, okay, this guy's stable. I'm going to really try and fail it, and I'm going to put a factor of safety of like 2. And what it does is it reduces the cohesion by a factor of 2, reduces the tangent of the friction by a factor of 2, and runs it again. Now let's say it fails. Probably it's going to fail. Factor of safety 2, right? So this one's good, this one's bad. So then it says, okay, I'm going to try 1.5. Same thing, right? Reduces the cohesion by a factor of 1.5. Reduces the tangent of the friction angle by a factor of 1.5. Runs it. Stable or not stable? Let's say this one's unstable. Okay, now it's going to try 1.25. Right? And just keep doing this. It's just a binary search. This one might be stable. Now it's going to do 1.3, whatever it is, right? And it just keeps doing that until it gets to a situation where it's one instance is just below stable and one instance is just above stable, and it gives you your factor C. So, you know, at a minimum, you're probably running 6 to 8, 10 FLAC2D models. Okay, so you can imagine if you had a humongous FLAC2D model, this could take some time, but not a huge amount of time compared to say 3D. So it is a realistic thing that people do in 2D, and it actually works pretty well.